Today we're going to talk about perpendicular and angle bisect. Our vocabulary for today is equidistant and locus. When a point is the same distance from two or more objects, the point is said to be equidistant from the objects, like equal distance. Triangle congruence theorems can be used to prove theorems about equidistant points. Here we have the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So in our picture we have xy perpendicular to AB, and therefore YA is congruent to YB, and XA is equal to XB. So the two red lines are equal to each other in measure, and they're congruent. The converse of the theorem states that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So if XA equals XB, then XY is perpendicular to AB, and YA is congruent to YB. A locus is a set of points that satisfies a given condition. The perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of the segment.
For this example, we're going to be constructing a perpendicular line through a point. In this case, we have point P. So this is our initial line, and we want to construct a line that is perpendicular to that, which makes a right angle. So what we do first is we put our point at point P. Once we've done that, we want to make an arc that goes all the way around from point P, from one side of the line to the other. It's okay if it doesn't go all the way around, but what you want to make sure you do is that the distance here and the distance on this side are both marked. So we can see that we have both of those areas marked. Now we take our compass and we put it so that we have a distance marked here. So we put our point where they cross at the intersection and draw an arc without moving your compass. I haven't changed this. We're going to move to this side where they intersect and put an arc. So we have an arc there, and just to check and make sure we didn't move it, that arc is right there. So now you connect with your straight edge from P to the intersection. So we connect right here from P to our intersection, and that should be a perpendicular line. So this should be a 90-degree angle, and if we want to double check it, you can use your protractor. Check here, we line it up, and it looks like it's 90 degrees. This is the exact same construction, if you notice, as constructing an angle bisector, except you have a straight angle. So when you have a straight angle and you're bisecting it, it makes two 90-degree angles, or a perpendicular line. So this is the exact same steps to follow as the constructing an angle bisector. Okay, now we're going to go ahead and construct a square. We start with a segment AB, which is going to be one of the sides of our square. What I'm going to do first is extend that line so that it is no longer a segment, but a whole line. So I'm going to go ahead and continue this and continue it this way as well, so that we have a nice long line that we can use. Okay, so now we have this line here that we can use, but AB is still going to be our side. So what we're going to do is start by drawing a perpendicular from B. So we go ahead and mark, just like we did on the previous example. We'll mark one distance here, and then go into the other side and mark the distance here, and then take our compass, put it at the intersection, draw an arc, intersection, draw an arc. Okay, so now we connect B to our intersection. I'm going to go ahead and call this point C. So we connect B and C, and that should give us a nice perpendicular there. So we have our first right angle for our square. Now we need to measure the side of a square, because a square has both 90-degree angles and sides that are equal. So we need to measure this and see how far up we need to go here, and it looks like our point was actually very close to where it should have been. I'm going to go ahead and put a point right there where that crosses. That's point C. So that's the second point, or the third point of our square. So now we're going to go ahead and do the same thing on this side. We're going to draw another perpendicular. So I'll measure this distance, measure this distance, make sure that these are both the same. They look pretty good. And then I'm going to draw my perpendicular. So do one arc this way, other intersection. Go ahead and draw this arc. Oop, my point moved, sorry about that. Draw a second arc there, and then connect from A to the intersect. So A is here, our intersection is right there. So we go ahead and connect those. And again, we're going to measure from A to B. Our side is that long, so I want to make sure I get it that long up here. And I measure how long that should be. And I'm going to put this as corner D, or vertex D. Okay, so now we have another right angle right here that we've constructed, another perpendicular. And the last side is going to be from C to D. So if I go ahead and take a look at this, I can see that all of my lines here, that's 2 inches, 2 inches, 2 inches, and 2 inches. Looks pretty good. And then I can see all of my angles if I measure them. That one looks pretty close to 90 degrees. That one looks pretty good, pretty close to 90 degrees. This one is 90 degrees, and this one should be 90 degrees as well. Okay, so that's how we go ahead and construct our square. You need to go ahead and draw a perpendicular at point B, a perpendicular at point A, measure the lengths of the sides, and put your points, and then go ahead and connect your top 2 points. So that's our square.
Here we want to find the measure of MN. The perpendicular bisector theorem says that MN is congruent or is equal to LN. We want to substitute 2.6 for LN, so we see that MN is also equal to 2.6. Here we want to find the measure of TU. The perpendicular bisector theorem states that TU is equal to UV. To substitute the given values, we find that 3x plus 9 is equal to 7x minus 17 from the picture. Subtract 3x from both sides, and add 17 to both sides to get 26 equals 4x, and divide both sides by 4 to get 6.5 equal to x. Now remember, we were asked to find TU, not find x, so we have to go ahead and plug that back in. 3x plus 9 is TU, so we plug in 6.5 for x, and get that TU is equal to 28.5. Remember, the distance between a point and a line is the length of the perpendicular segment from the point to the line. The angle bisector theorem says that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So AC is equal to BC. The converse says that if AC is equal to BC, then the angle APC is congruent to angle BPC. Based on these theorems, an angle bisector can be defined as the locus of all points on the interior of the angle that are equidistant from the sides of the angle. Here we want to find the measure of BC. The angle bisector theorem says that BC is equal to DC. So if we substitute 7.2 for DC, we find that BC is also equal to 7.2. Here we want to find the measure of angle MKL. Since JM equals LM and JK is perpendicular to JM, KL is perpendicular to LM, and KM bisects JKL by the converse of the angle bisector theorem. If it bisects JKL, then we have the definition of angle bisector saying that the measure of angle MKL is equal to the measure of angle JKM. Substituting the values from the picture, we get 3a plus 20 equals 2a plus 26. Subtract 2a from both sides, and subtract 20 from both sides to give us a equal to 6. We need to find the measure of angle MKL, which was equal to 2a plus 26. So we insert 6 for a, and get 2 times 6 is 12, plus 26 is 38. So measure of angle MKL is 38. Here we have a picture where measure of angle WYZ is 63 degrees, and XW is equal to 5.7, and ZW is equal to 5.7, and we want to find the measure of angle XYZ. The measure of WYZ plus the measure of angle WYX is equal to the measure of angle WYZ. We also know that the measure of WYZ is equal to WYX because of the angle bisector theorem. So we substitute, finding that measure of WYZ equals the measure of XYZ. We simplify it, and this we kind of know intuitively. I know we had to go through 3 or 4 steps here to get this, but twice one of the smaller angles, if it's bisected, twice one of the smaller angles equals the big angle that was bisected. So we kind of already knew this rule, but we had to go through these steps to be able to geometrically show that. So we substitute 63 for WYZ, because if one side is 63, the other side is 63. 2 times 63 is 126 degrees. So XYZ is equal to 126. Here we want to write an equation in point-slope form for the perpendicular bisector of a segment with endpoints 5, 2, and 1, negative 4. So first we graph PQ. PQ looks like this. The 2 yellow points are the endpoints P and Q. The perpendicular bisector is perpendicular to PQ at midpoint. So first we have to find the midpoint of PQ. The midpoint formula is what we're going to use to do that. The first point was 5, 2, and the second point 1, negative 4. So we add the x's. 5 plus 1 is 6, divided by 2 is 3. And the second point, the y's, are 2 minus 4, which is negative 2 over 2, which is negative 1. So our midpoint is at 3, negative 1, and we can see that in our picture. To find the slope of the perpendicular bisector, we use our slope formula. Make sure that you remember this formula because we will be using it over the next couple of weeks with our coordinate proofs. The slope of PQ is negative 4 minus 2, which is negative 6, over 1 minus 5, which is negative 4. Negative 6 over negative 4 reduces to 3/2. Since the slopes of perpendicular lines are opposite reciprocals, make sure you know that too, opposite reciprocals, the slope of the perpendicular bisector is negative 2 over 3, and that's the opposite reciprocal of 3/2. Now we have to use point-slope form to write an equation. The perpendicular bisector of PQ had slope negative 2/3 and passed through the point 3, negative 1. So we use point-slope form and plug in the numbers that we know. We know that y1 is negative 1 from above, m is negative 2/3, and x1 is 3. So we substitute. Now we're going to simplify that double negative in front of the 1 to be y plus 1. And then we can graph our line, and we can see that that does look like a perpendicular bisector. Here's your lesson quiz. Go ahead and try some of these problems, see how they go, and if you have any questions, please ask in class tomorrow.